Well, we're going to talk about crystals. We talked about there are amorphous solids and crystalline solids have a long-range order to their atoms or molecules. How do you even explore how those atoms or molecules are arranged? You do that using X-rays. The beautiful shapes that we see, I think these are quartz crystals. This is a snowflake. There is a chemical reason that snowflakes always have 6 sides. It's because of how the water molecules arrange to maximize the hydrogen bonding when they freeze to become a solid. And all of these beautiful shapes that we observe in crystals of all kinds are due to the arrangements of the atoms or molecules inside. So we talked about electromagnetic radiation, and we talked about how you can have constructive interference between 2 waves that causes the amplitude to get larger, or you can have destructive interference that causes those waves to essentially cancel each other out. And that when we have light passing through 2 slits, where the distance between the slits is similar to the wavelength, we can get interference patterns. Remember the guy with the box on the beach, right? Here's the interference patterns. Well, the atoms within crystals have spacings of about 100 picometers. And that is similar to the wavelength of X-rays. X-rays are electromagnetic radiation. We just can't see them with our eyes, but they behave like light does, and they create interference patterns as well. So X-ray crystallography involves taking an X-ray source, passing that through a small hole so that you get a focused beam, and then passing that beam through a crystalline solid. And as that goes through the spacing between the atoms or molecules in the crystal, those spacings are small enough that they act like that double slit experiment and give us a diffraction pattern. By analyzing the diffraction pattern, we can find out what the spacing is and what the arrangements are between the atoms. And we can identify the structure of them. Now, you can imagine that involves a fair amount of math, right? That's not something that you just set out to do one day. It's rather complicated, but it's really, really neat too. So we'll just look a little bit at how this works. So 2 waves that are in phase. So these rays coming in are coming from the same source. They are in phase when they come in. They will have constructive interference if the difference in the path length is an integral number of wavelengths. How best to explain that? Well, let me try. So let's imagine these guys are coming in phase, right? And we've got wave 1, wave 2, and wave 3. And this ray, ray 2, is going to travel farther because it's going to go through the first layer and hit the second layer and bounce off. So it is going farther than ray 1, which is bouncing off this first layer. So what happens then is here we have, oops, ran out of space there. 1, 2, 3. Now this is 1, 2. And so ray 2 gets offset by 1 wavelength from ray 1. They are still in phase, and so they will have constructive interference. So you'll get a bright spot or an increase on the detector when those hit, compared to if it's somewhere in the middle, if it's like half, then you'll get destructive interference and nothing will come. You won't see anything. Does that make any sense? So if the distance traveled by ray 2 is an integral number of wavelengths, so that they're still in phase when they reflect off, then you'll get constructive interference. Well, we can observe the constructive interference. So this involves a whole bunch of geometry, which, if you're interested in that, is awesome, and if you're not, is terrible. Here, D is the spacing between the planes of the atoms. And here's this angle. They're coming in at an angle theta, and then they're going to leave at an angle theta. And so this distance that the ray 2 travels, it travels this much extra and that much extra. So it travels 2a. So we want 2a to be an integral multiple of the wavelength. And so you take the sine of theta, and that's going to be a over d. So the sine of theta is a divided by d. And then a will equal d sine theta. So now we've got a, and we plug that in here, times 2, and lambda equals 2d sine theta. And this is known as Bragg's law. If there's a Bragg's law question on the exam, I will give you the equation. N is an integer number, 1, 2, 3, 4, 5, doesn't matter. Theta is the wavelength. D is the distance between the atomic planes, the layers of atoms. And theta is the angle at which the X-rays are coming in. Any questions? So typically what they do is you shine the X-rays on this crystal and you vary the angle. So imagine shining the X-rays and you move the angle. And as you move the angle, you see that you're getting either a bright spot or a dark spot. You see that the interference changes. So you can measure the angles at which you get constructive interference. So the angle, theta, we can calculate the distance between the layers of atoms that way. Does that make any sense? I mean, how else are you going to measure the distance between two things that are too small to see? That's kind of tough. X-ray crystallography has been used to study a lot of things. The double helix structure of DNA was discovered using X-ray crystallography. And this is a picture of the diffraction pattern that was seen. Now you look at that and it really just doesn't make much sense at all. You have to study and understand exactly how the instrument works to do that. But you can study proteins, you can study all sorts of interesting biological molecules, you can study simple atomic lattices or various crystals that you might find in nature, all kinds of things. So let's practice using that equation. So again, the equation is n lambda equals 2d sine theta. So n lambda equals 2d sine of theta. So the question is, the spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So when they say the spacing between the layers is this, that's D in the equation. D is the spacing between the layers of the atoms. So that's D right there. We're supposed to calculate the angle, so that's theta. 154 picometer X-rays. What is this? That's the wavelength. That's the wavelength of the X-rays. Well, I'll just write it over here. Lambda equals 154 picometers. And we're supposed to find the angle where we get a maximum reflection, where we get constructive interference for n equals 1. So we know what n is, we know what lambda is, we know what d is, we need to solve for theta. So I'm going to rearrange the equation. We'll get sine of theta is equal to n lambda divided by 2d. So I took both sides, divided both sides by 2d. I isolated sine of theta. So I'm going to calculate what that number is. So n is 1. Lambda is 154 picometers. 2 is just 2. And the distance between the layers is 157 picometers. The picometers cancel out. The unit there is not important as long as both of those are in the same unit, so the units cancel out. So then we've got 154 divided by 2 divided by 157. And so that's going to equal 0.490445586. No units. That's the sine of theta. If we know what the sine of theta is, how do we find out what theta is? The inverse sine. So theta will be the inverse sine of that number. Oops. I don't know what I'm doing. 490445586. So my calculator has a button for that. So put that in there. And I come up with theta equals, and of course I've got all these digits, right? Angles, these are measured in degrees, so it's that many degrees. Again, we can't really do significant figures with sine and inverse sine, so then we just try to be reasonable. What might be a reasonable number of significant figures here? 3 is probably a good idea. So we'll say, because that many digits is ridiculous. So we'll say, well, it's 29.4 degrees. So that's the angle at which you would expect maximum reflection for molybdenum. Any questions? So doing problems like this really comes down to remembering what the letters stand for in the equation. I'll give you the equation. And then being able to pick the information out of the words that are given to you.